Welcome everyone to the online class of CSE 4551 Computer Graphics and Multimedia. Before the onset of the COVID-19 pandemic, we have finished up to color and color spectrum. From today, we will be starting with collision detection and response. Okay, let's move on. What is collision? First of all, when we consider our previous content, we've already seen how to model a virtual scene using curves and surfaces and how we can define its transformation. But in order to define the physics of the scene and make it seem realistic, we need to perform collision detection and apply appropriate responses to them. Otherwise, we will have a scene that is only visually present, but it will act like an immaterial ghost that can pass through anything. Collision is allowed only when an object is defined as a rigid body. This lecture discusses about how basic physics can be incorporated into a virtual scene through collision detection in order to make it seem more realistic. In terms of physics, we know collision as the event of two bodies coming in contact with each other. But in the field of graphics, we define all bodies in terms of curves and surfaces. Hence, collision here must be defined in terms of shapes. So in graphics, collision is said to occur when the shape of two rigid bodies are intersecting or overlapping. Or in other words, the distance between the shapes fall below a very small tolerance value. So how do we detect collisions? We may define the objects of a scene using implicit equations. As an example, the implicit equation of a sphere would be h of x y z equals x square plus y square plus z square minus r square equals 0. Detecting collisions for such surfaces defined by implicit equations is easy since we can immediately find for any point x1, y1, z1 that h of x1, y1, z1 is equal to 0 means this point is on the surface, and the functional value is less than 0 means the point is inside the surface. So, but this becomes more complex when we are dealing with other types of surface representations like meshes. It is not really known whether the mesh is even closed or without any boundary. Collision response for particles. The simplest collision response we can consider is when a particle in motion hits a stationary plane surface. If the corresponding velocity of the particle is represented by v, then we can decompose the vector into two components at the point of collision, as shown here. One is the tangential component vt, which runs along the plane surface, and the other is the normal component vn, which is perpendicular to the plane surface. If we think of a real-world scenario where we throw a ball at an angle towards a wall, the ball bounces back from the surface of the wall, maintaining an angle that is similar to how the phenomenon of reflection of light occurs. But it is important to note that unlike the reflection of light, the angle at which the ball is thrown is not exactly the same angle at which it is reflected. This is because the collision of the ball with the wall is not a perfectly elastic collision. The ball does lose some of its energy upon hitting the wall due to it being converted into heat and sound energy. Let's ignore air resistance here. This particular case is handled by a quantity called the coefficient of restitution, which we denote here as epsilon. This is the ratio of the final to the initial relative velocity between two objects after they collide. The reaction force from the surface comes perpendicularly in the opposite direction. So basically the negative of the normal velocity is the one responsible for reflecting. As you can see here, v equals vt plus vn, but later when we are considering the reflected velocity, we are taking minus here. This is because the inverse of vn, the reverse direction of vn is working here. That is why the negative. And the coefficient of restitution acts as a weighted sum of Vn and Vt. Vt is always 1 because this will not change, but Vn, how much of Vn is being used to provide the opposite velocity is going to be determined by epsilon. Okay, so the reaction force from the surface comes perpendicularly in the opposite direction as we have said before. So basically negative of the normal velocity is the 1, responsible for reflecting, whereas the tangential velocity remains unchanged. Thus, we can model the collision response for the particle moving at velocity v equals vt plus vn, so that the reflected velocity will be v equals to vt minus epsilon vn. The value of the coefficient of restitution can be from 0 to 1, and it is 1 when we are considering that the collision is a perfectly elastic collision. Then the corresponding reflection will be a mirror reflection. Now we come to a problem that occurs most of the time while detecting collision responses, and that is the overshooting problem. In reality, we cannot have two rigid bodies overlapping one another, since we cannot have two masses occupy the same volume at the same time. But in the virtual world, this is a common scenario, since the detection of collision takes a small amount of time, and by this time, the bodies have already passed a bit through each other. This is basically the problem of overshooting. A possible solution to the overshooting problem is to back up and compute the intersection point and apply the response there. But a more optimized way is to approximate it by simply projecting it back to the closest point of the object, as it is shown here. Uh, this is not the exact solution, since we cannot find the exact point at which the collision occurred, but most of the time this provides a small computational time boost. That is why we ignore the small inaccuracy that comes with it. Okay, now we move on to collision detection in big scenes. Suppose there are n objects in a scene, and we consider the scene to be large when n is fairly large. Usually we need to perform collision testing in every frame, where in a typical scenario, 1 second will have 60 frames. Uh, that is, if you're considering 60 hertz refresh rate. So we would need to check for collision 60 times within a single second. If we had to perform pairwise collision testing between every pair of objects, then the cost would be big O of n square, as shown here, which is quite huge when the number of objects in the scene is large enough. A simple optimization here would be to separate the static objects from the dynamic objects. If you notice, you'll see that most of the objects in a scene are basically either background objects that only add to the aesthetic of the scene, or they are interactable objects that do not interact themselves. A few key objects in a scene are the moving and interacting ones, and these objects should have a separate definition so that the collision testing coroutine targets these objects separately. Then the problem reduces to checking the pairwise collisions between every pair of dynamic objects and whether those dynamic objects have collided with any of the static objects, resulting in a cost of big of static times dynamic plus dynamic square. This is how we get this cost, which is, but this is also still quite huge. So we move on to a more optimized way to detect collisions, which is known as hierarchical collision detection. Trying to detect collision, considering the actual complex mesh of each object, is difficult. As we have mentioned before, recall that detecting collisions from implicit equations is easy, but for complex, but for meshes is going to be complex. So here we consider the simple shapes like bounding spheres as representatives for the collision volumes of each of the objects, because spheres or boxes are a lot more simpler than complex meshes like human body shapes. So an object is said to collide with another object when their corresponding collision spheres or boxes collide. This is the first consideration for hierarchical collision detection. Then the second consideration is to perform recursive hierarchical testing, that is, to spend time only for parts of the scene that are close. Here, by time we mean computation time. And we are checking only, we are spending time only for the close ones because those are more likely to be involved in collision rather than the ones that are very far apart. This drastically reduces the cost of collision detection, since now we don't have to perform collision test for every pair of objects. Another reason why this is so fast is because we are using simple shapes like spheres or bounding as the bounding boxes. And we know that sphere-sphere collision test is easy. How can we do that? Suppose we have two spheres with center uh, C1 and C2 and radii R1 and R2 respectively. We can easily check that they are intersecting if the distance between the centers is less than the sum of the radii. That is, the distance between the centers, denoted as absolute, the magnitude of C1 C2 is less than the sum of R1 plus R2. Now we come to the main reason why it is called the hierarchical collision detection. The reason is because we are maintaining a hierarchy of bounding spheres organized in a tree-like structure. The whole object is encompassed by a large sphere, and this large sphere contains some smaller spheres, which will be acting as the children spheres, and they themselves act as bounding spheres for some parts of the object. And when we find collision of one sphere with the larger sphere, for example, this large sphere collides with the collision sphere of another object, only then we go on to find out which of its children spheres are closest to the other sphere that it is colliding with. And we do this recursively until we reach the exact body part or the exact part of the object where the collision occurred. Okay, now we move on to the construction of the hierarchy. Well, at first we can see an example of what the hierarchy would look like if we consider more and more detailed levels of collision spheres. Using only a few collision spheres would result in bounding boxes, a complex bounding box like this, which is still not complex enough. If we want to define the mesh in a more detailed manner, we have to use even more collision spheres within it, and we can get even more accuracy by using even more bounding spheres. These pseudocodes are not necessary for memorization, but it gives you an idea of what the implementation of such a collision detection algorithm would look like. Feel free to look this up if you are interested. Here, simulation is shown of where this particular pseudocode comes in use. That is, suppose we have one object which is the bunny and another object which is the teapot, and we have their separate bounding spheres. The collision detection would start from the large bounding spheres, which would find that they are colliding because there is some overlapping between them, and then from that, the first bounding sphere has some children spheres, some smaller children spheres, and among them the one that is closest to the larger bounding sphere of the second object is this bounding sphere. So this is detected, and then similarly from the second object, among the all children spheres, the one that is closest to the black bounding sphere is detected, which is red. And in this way we can recursively move around and find even more other children spheres that would be close to the sphere of the red sphere, and in this way we can find out exactly at which point the collision occurred. Okay, and there are other options other than considering bounding spheres as the collision boxes, and these would be axis aligned bounding boxes, uh, oriented bounding boxes, and binary space partition trees. These are not exactly part of our discussion, but if anyone is interested, they can look up R trees, OBB trees, and KD trees. Okay, now we move on to hierarchy construction. Uh, there are three types of hierarchy construction methods, which is top down, bottom up, and incremental. We have discussed before that we need to define a hierarchy of bounding spheres to represent the collision volume of the objects, right? This hierarchy can be constructed in these three ways. One is the top down, which is the divide and conquer approach. Here we recursively break down the scene into separate sections and build spheres around them. In bottom up, we build small spheres for every individual objects and then recursively cluster nearby objects into larger spheres, connecting them as a child sphere to the larger parent sphere containing them. In the incremental method, we take a large sphere encompassing all the objects as the root, and then add new spheres encompassing individual parts of the object as children to the root. In this way, we add objects one by one, binary tree-like style. But we will be mainly discussing the first top-down divide and conquer approach in our lecture. Okay. So at first we need to define what is a bounding sphere of a set of points. Given center C of a sphere, the radius of the sphere would be found as maximum of C minus pi. That is the point which is farthest from the center. That particular distance would be considered as the radius of the sphere. Uh, Okay, so once we know how the center and how the radius will be defined, now we need to know what the center will be found as. So using axis-aligned bounding boxes, if we were to use axis-aligned bounding boxes, then center would be found as x mean plus x max divided by 2. Similarly, y mean plus y max divided by 2, and z mean, this would be plus. Okay, not comma but plus. Z mean plus z max divided by 2. So that would define the position of the center at which we will consider from which we will consider the bounding sphere, and the radius would be found as we discussed before. That is the distance between the center and the farthest point. Okay, now we come to how the top-down construction would be done. The top-down hierarchy construction of the bounding spheres. Here, as we have mentioned, there are three ways of constructing the hierarchy of bounding spheres, and we'll be discussing only the top-down construction method, which is quite simple and consists only of 2 steps. But the key here is to understand that these 2 steps will be performed recursively. These 2 steps are take the longest scene dimension, that is, take length if the length is longer than the width. Then cut along the dimension, assign each object to 2 sides. That is, if we were to cut lengthwise, and then we have to assign all the objects to one of the 2 sides, either the first half or the second half, and then we build spheres around them. That is, after the first step, when this is done for the very first time, we will have 2 halves of the scene, and we will have 2 bounding spheres for each half. Okay, these steps are performed recursively. So as we have said, we will after the first loop, we will have 2 halves. Then we will again divide each of the halves and have spheres for each of the objects in the resulting halves of the previous halves. That is, this half and this half will again be halved themselves, and then they will have separate bounding spheres for each of the halves. Okay, so thank you everyone. This will be the end of the lecture for collision detection.